So I think we can start. Okay, hello everybody. Welcome to my session. I hope you like the Postgres Open. It's lots of interesting content, and I hope you will not be bored during my presentation. So, hacking with PostgreSQL for fun, not so much profit. So, unlike the title suggests, it's not going to be about password cracking, abusing privilege system, or security. It's going to be rather deep dive into the world of Postgres stored procedures. My session will be accompanied with background projects with 2 PostgreSQL servers and lots of demos. And during the presentation, I will show you 2 products. One product is an example application that is completely 100% written in PGSQL. And this is a very non-typical application because it is a game. So why game? For fun, because it's fun to have a game solver inside database. And some other reasons will become clear during the session. And the other product is extension written in C that will help me, facilitate me to solve this game more efficiently using 1 or 2 hosts. So this is the agenda, and I will leave the agenda slide open, and I will tell you some words about me and my company. So my name is Piotr Jarmusch. I've been working for the last 8 years for the company called Allegro PL as a senior database developer, administrator. I started my IT career as a developer, writing in C, Java, Perl, and Python. And many projects I've been using databases, but I always blaming, because I didn't understand really how this works, blaming database for being slow. Until one project, I was asked to look at the database from the administration point of view, and I had to deep dive in the core and understand the beauty of SQL and the power of transactional layer. And I fell in love immediately with databases, and this feeling lasts until today. And about my company is an online marketplace, the biggest in Poland. We have 20 million users. The company started 19 years ago and was growing pretty much 20% each year and every year. And about 6 million users, active users doing transactions, selling and buying stuff. Allegro has been recently purchased by 3 funds, Permira, Sinven, and Mid-Europa, for $3.2 billion. So it's quite lots of money in Poland and in Central Europe, maybe in the US not. And having 20 million users, you have to have pretty hefty data structure for infrastructure for databases. And for this, we are truly multi-culti, having Postgres, Oracle, MySQL, and also Cassandra and Mongo. We have Exadata and 1 petabyte Hadoop Spark cluster. But recently, we have chosen Postgres because, as everybody here probably, we want to ditch Oracle. And Postgres seems to be the best candidate for that because its spirit is very similar, and it gets more and more features that can replace what Oracle offers. And we are an on-premise company. We have 2 data centers, about 15,000 servers, and we do regular switchovers. And recently, we are going cloud. And we used to use Amazon, but Amazon is our competitor. It's not existing really right now in Poland, but it may soon. So we chose Google GCP. And if I were to describe my company in one sentence, it is like eBay plus Amazon scaled down to a country like Poland. So it's pretty big. Okay, first I want to introduce the world of stored procedures in Postgres and some history. And first, how developers see RDBMS versus what really is. I recently, most often I encounter developers that they treat databases as a dumb data store which has only tables, indexes, and they throw SQLs at it, and the database throws results back. And this is like 10% of the functionality. But developers don't understand this. Even if they know that you can have stored code, they treat it like some kind of exotic feature, unless you show them that you can solve lots of problems with that. But in my opinion, that's what really truly distinguishes dumb data store from the powerful computational environment is ability to run the stored code. So Postgres is unique even in the RDBMS world because it offers like 2D-dimensional extensibility. You can create language. I don't know in another database that you can create language. Within the context of this language, you can create procedures. And Postgres supports many languages. One prominent is PostgreSQL, which happens in the course in 1998 in version 6.4.1. It is loosely based on Oracle PostgreSQL. And those two languages, on the other hand, were used as basis for ANSI SQL PMS standard, the recommendation for stored code inside databases. PostgreSQL supports functions, procedures, triggers. It is a fully fledged procedural language which supports conditionals, loops, recursion, exception handling, rich data types which are supported directly by the database. And you can do a lot of things in using this language. It also, because it runs in the database, it is already connected, so it's very super easy to access data tables. You can use selects, you can use cursors and process rows by row, and any other DML. You can use dynamic execution or even prepared statement. And so the one distinction between functions and procedures is that it didn't really existed before 11, and 11 makes a distinction. Functions are like returning values and are not supposed to change the database state. Procedures can change the database state, and what's more important, they can control transactions. Functions can't. And in version before 11, in order to control transactions, you would have to use some tricks like DB links to connect, make another connection to the same database and process it transaction-wise, some large batching process. Or just move the code outside of database from cron, for instance. There are some reasons why you should actually use PostgreSQL, because first, it is reduced network traffic. You can put 2 inserts and 1 update in the body of the function, and the client application will call it only once. So you can save on 2 traffic rounds. And this is especially true in the case of ETL processes, where you can potentially extract and transform and load hundreds of gigabytes. And even if your network has latency under the millisecond range, it adds up and can be hours. So the processing should be locally to the data as close as possible, because this part will never be enhanced because speed of light is finite and will not change. The other reason is encapsulation. So you can isolate the application code from the database layout. You can transparently change the implementation without application even knowing it. And security, because to some extent it protects from SQL injection, because database procedures are strongly typed. There are many other reasons, but I think the 3 are good enough. PostgreSQL offers many built-in functions for string manipulations, data, numeric types, and if it's not enough, you can always go down to the low level and write a C function in the form of an extension. There are tons of extensions for Postgres, and yes, I will be using one in this presentation. So if you want to learn about stored procedures, I recommend official documentation for this or many tutorials. And as always, it is good if you just start programming yourself. Okay, so now about our application. So what is the game is called Wordament. It is the blue square is official logo. It is originally written by Microsoft and become immensely popular with the advent of mobile devices and with touch interface. It displays you a board, originally 4 by 4, with random letters and random numbers in it. And the goal of the game is to find as many words as possible. And the example, you start with the letter C and you find a word card. And you have 2 minutes for the solution. There are some constraints, like the minimum length of the word that is accepted is 3 letters, and you cannot reuse the current, in the current search, the tile is already visited, so you can use cycles. A good example would be the 3 letters B-A-N, and you couldn't use it for banana because you would have to revisit 2 letters. And the game is great for learning new words, of course, because even many of you are native speakers. I bet you wouldn't know many of words that this game can produce. Okay, so as I told you, this implementation is 100% in PostgreSQL. It is it's composed of many functions, several functions and procedures that work in concordance and solve the problem. Some data structures are using local variables, current word that is being built. Start with an empty string, and as the algorithm progresses, it appends letters picked up from the board. The board itself represents the state of the game. I'm using temporary table, which is session scoped. Similar session scope is solution table for found words. Whenever I find a word, I insert in this table. And also there's a dictionary for checking valid words, which is regular Postgres table. The algorithm is a depth-first search tree with dynamic decision pruning. It sounds complicated, but it's really simple recursion. And the game itself has complexity exponential. So it grows very quickly. The number of possible words grows very quickly with the size. But this decision pruning, it helps to keep the runtime short. So I extended the game using native support for Unicode in Postgres. So we can actually use this solver to learn Spanish or French if you like. And this is one sweet one-liner which I used to load Russian dictionary into Postgres table. One liner, one transaction. So how does it work? The main interface function is called play. It takes one string parameter and returns a query. It's a list of found words. The string is formatted in a special way that has 4 segments separated by white space. Each segment represents 1 row on the board. And when I'm preparing slides for this presentation, I was looking for some picture. I find this one. Of course, out of curiosity, I ran my solver on it. When I saw the solution, I thought it was an excellent example. So let's hit enter. Okay. So it found 275 solutions, words. And one word stands out distinctively, and you can see the path the algorithm had to follow to find it. And okay, now it's time for demo. So I can show you exactly how this works. I have here an open session to Postgres database. And yeah, and let's run exactly the same example. Yeah. Although we can have another example. Now this time it's a little bit more, and yet another, which is like the alphabet, ABCD. So it was not very much. And the algorithm is universal. I can support many languages, as I told you. It works on view, so I can repoint a view to, say, German. And if there are any German-speaking persons here, so you can check if the words are correct. So you have the umlauts. So I didn't have to change anything. This supported out of the box. And also Russian. And similarly, I could use any language, so French and Spanish. Even I think Chinese would work, although they have different, they read top down, I think. Okay, let's point back to English. And the next slide, here is the slide when I can actually explain why I have chosen the game, because games are, although they seem trivial and frivolous, they're not really not. There's branch of mathematics, game theory, which has lots of practical applications in economy, military, and they have one cool feature: they're easily parallelizable. So sometimes those problems are called embarrassingly parallel, and the game ornament is not different. It has inherent parallelism. So remember, the algorithm uses the search tree, and as any other tree, a tree has to have a root. And those roots are simply one letter on the board. And there are actually up to 6 independent search trees that can be running in parallel. And so, and before we go back to, okay, I can show the code for because it's just really one page. So this is the main algorithm functions. The working horse, it's called try. It takes integer, which is the size of the board, the string, which is the current word, and the coordinates of the tile, which is going to be tried. So at first, we are trying to see if we're not out of the board, and if the current tile is not occupied. If not, then we pick up the letter from this tile and append it to the string, and we check if it's candidate. This is actually the part where the pruning happens, because if the word is candidate, that means that it's prefix of some existing word. If it's not, then there's no more sense going down this path. And if it's candidate, and it has the constraints that the 3-letter long and also a perfect match, because it can be a word like chair and chairman, but in between there are no words, so we have to check both. We enter in the solution, and then we try recursively every other possible direction. And finally, this is a backtracking stage when we leave the current tile. And this is, and this one is actually the serial version. So you can see this is a double loop. It calls perform 16 times. And this actually is generic, because I have extended the game. It doesn't have to be 4x4, so I have used parameters for this. And before we modify the code so that we can run it in parallel, let me go back to the slides. And yeah, and define execution context in Postgres. And Postgres is a multi-user and multi-processing environment, so obviously it has many execution contexts. But in the simplest approach, each PostgreSQL session constitutes an execution context. So I could manually run this individual search trees in 16 independent sessions and collect the results and have the solution. But I like Postgres, and I like threads, but we lack thread support in Postgres, so I decided to combine them and create threads in Postgres. You cannot do it using PostgreSQL. You have to go to the C level, which is pretty powerful, and you can do everything, but you have to be careful, because the C level can corrupt your database. So with great power comes great responsibility. So I defined the abstract API. It's borrowed from POSIX threads, because I have background in POSIX and thread and Java threads. So there are 4 primitives for managing threads. And create thread, which takes a name, which serves as a purpose of a handle. So you give the name and refer with the name to next other primitives. There's a thread procedure, which is actually a simple either built-in or user-defined PGSQL procedure. It is actually a string, and the string can look like a call, so you can use parameters as well. And there is third parameter, hostname, which is default null, but I'll explain it later, what it does. The other primitive is start thread. So create thread, create some abstract execution context, and give it the names, and can give it the code. But it doesn't do anything else. The start thread actually kicks the code, so the thread runs in background. The start thread call is not blocking, so it can return and start another thread. The third primitive is a join thread, which is used like rendezvous. So if you call it, it will block until the named thread finishes execution, and it can collect information of outcome of the execution. If there are any exceptions, errors, it will return it. And finally, you have to clean up after the thread. It's called destroy thread. Arguably, you could combine those create and start in one call and join and destroy in another call, but I like to have some flexibility, and you can always create a wrapper around that. So this is some details about implementation. So the extensions, writing extension and Postgres is, especially at sea level, it's a topic in itself. It would take perhaps hours to explain it, but technically it is a shared library, which is loaded into the memory of the process, of backend process, and there is a way in Postgres to map PGSQL symbol to exported function from that. So I'm using libpq client library, which is the standard library for coding clients in C for Postgres. I'm using asynchronous query execution, which lets me doing things in background and non-blocking calls for starting thread. I'm also exposing the thread state via regular table thread list, so you can monitor the thread list, how they progress, how they change the state from another session. And of course, I didn't invent threads, we didn't recode Postgres core. I just used something that existed. So I'm using backend processes as thread containers. So each thread has state. There are 3 states I have defined. It's created after the create thread returns, running when the start thread kicks off the thread procedure, and finish when it finishes. These APIs in Status and Sandy, it's working in progress, so it may change in the future. I may use some other calling convention, not use a fixed name for the thread, but rather opaque handles. And as in threads, you have thread local storage and some shared data. So how this is emulated in Postgres, so data separation is at local variables because they are local for a stack, and local temporary tables which are private per thread. And data sharing using regular Postgres tables. And what is fine, what I find interesting here, that normally when you program threads, you need to do a locking, synchronization, and stuff. I don't have to do it because it's Postgres. It's already doing it because it has transactional layers. So the logs and MVCC and any other features are working for me automatically. Okay, time for demo. So okay. So I will use, I will call each of these primitives in one step after another, so I can show you how the state changes, and we can monitor it from another session. So let's, the thread procedure here is, I'm sorry. Thread procedure is a built-in PG sleep, which takes an argument 10, so it will be sleeping 10 seconds. So let's create it, and let's see what happens here. So this is thread list table, And this table shows you that there's the name of the thread, the state that is created, the host name that is created on master, CTS, it's created timestamp, CID is a connection ID. It is actually a bit of a backend which implement this thread. And what is 357? So we can see there is a backend, Postgres backend that is simply created right now. Let's call start thread. And let's go to monitoring here. So we see that state changed to running and there's start timestamp, and we can keep on refreshing, and the state's changed to finish. So this sleep simply completed. And we have also the exit code 0 because there was no exception error, no error message. And I also have the end timestamp, so we can just take time, compute the execution time from these fields. And one interesting thing is that in my thread API, I built in some logging. So this is actually how the call looks on the backend side. So it is like it starts with a transaction, then there's an anonymous block, which defines an exception handler. There is a call to pg sleep, and there is some post start call, which is it's a state management. So if there is an exception, we are giving the exit code 1 and SQL error message. If there is no exception, it is simply a 0. Okay. And so the exit code is 0, and the join, if we call join now, it should return 0 for as an exit code from the thread. And finally, we can destroy the thread, and it should disappear from the table here. Right. So here another example, this time with idlers. So I have created this simple PostgreSQL which does idle loop, and we can just copy and paste this, the whole thing, and we can see here. And we can monitor. Okay, so maybe one more time because it was too fast. Running, finished, running, done. And we can also observe it from the operating system. Once again. And you can see two super active Postgres processes burning CPU. So actually threads is running. Okay, let's go back to presentation. Okay, so right now we have created this facility for running threads, but we have to now refactor a bit the code. So I used because we have possibility to run this. Let me. Okay. We have possibility to run that in one thread, which is the whole partition of 16 roots, or we can use two threads and have 8 partitions. And you can, and the extreme case is like 16 threads, and each takes one thread. So the easiest way is to create something like play range, which I'm introducing linear addressing for this. So I'm counting tiles from top left to starting from 0, 1, 2, 3, 4, and 16, and at the PostgreSQL level, I defined the function which is called playRange, which exactly takes the initial index of the tile and the final, excluding so it defines a range or partition. So this way I can mix and match the partitions to the number of threads. Okay. And now having this, so the code has changed a little bit because we have now introduced one data structure. This is the G solution, I call it. It's a regular Postgres table because the former serial version uses session scoped table for solutions, and those partial solvers will use the private local session for solutions, and finally they will insert all the local solutions to the global table, and this global table will collect all of partial information, partial solutions. So, and if you have some background in thread programming, there's usually an approach where you have one controlling thread and couple of worker threads, and these controlling threads have some tasks to do. It divides the task and hands each thread a piece to do. And the code for the parallelized version, which looks similar to its serial brother, but it takes another parameter. This is the integer which specifies the parallelism level. And it has 4 loops for each thread management call. In one thread, we create those partitions, and you see we are creating the call to playRange from using the string, initial state of the board, and using the from index and to index. And we are doing this n times as many execution levels, execution threads we can create. Then we start, and then we join them, and then collecting the information. And finally, we destroy them. And using the G solution, we display them their what they've produced. Now let me do an example. This is a fun part, actually. You can play with parallelism and see if this scales. Okay, so this is the initial example with from the slides. Let's run it with default 1 parallelism level. So it's the time is exactly almost exactly the same. This time is different because the G solution table has to be cleaned after the call, because then it was local table, so we are truncating it. Now you have to truncate it by hand. So we have to clean state for another run. Okay, let's try with 2 threads. So it's almost twice as fast. And it produces exactly the same result set. Maybe 3. So it's still faster. 4. Yeah, it's actually stopped. We can try with 8. Now we didn't see much improvement now. And this is because this is a virtual machine which is defined in a background project with 4 CPUs, so you can expect a linear scaling up to the number of CPU resources are exhausted, because most of the time this is a CPU-bound process. And this thread management has its own non-zero overhead, so if you overshoot the parallelism level, it actually works worse. This is very short, so I have some other examples with larger sizes, and we can test this. Here, the speed up will be more visible. I started with 2 because one it would take 25 seconds, so I don't want to wait. So it's 30 seconds. Oh, I'm sorry, I forgot to truncate it. Once again. Yeah. Truncate. Then let's 4 threads. It should be about 6 seconds now. Yes. And maybe 8. Yeah, it's too faster. And let's get crazy. Yeah, it worse actually. So it would be about 4, 6 because this is the around the number of CPUs for our machine. Oh, let's go back to presentation. And this is actually a visualization of what this happened. So we had one server for CPUs and some number of partial solvers. So each solver solved it, private set of roots, and those partitions cover the whole board. And okay, so let's go next slide. So next natural question will be, can we extend it further? Because so far we showed that it scales up. If we give it bigger machines with more CPUs, we could probably scale better. But scaling out is better than scaling up because scaling up is limited by the physical size of machine. You can theoretically build a 10,000 CPUs machines, but it will be unusable because single image operating system would be clogged with supporting threads. So actually it's better to have commodity hardware and connect them with a fast 10 gigs Ethernet and use that for solving parallel problems. So there is another machine running on this project, and it is using PGLogical. It is almost perfect copy of the master, but in this PGLogical, it doesn't have to be exact copy. The most important thing that is that it should have the same tables for dictionary and the code. The code has to be the same. And I'm using for data transmitting data from master to slave. I'm using publication and subscription. So I define actually 2 publication subscriptions. One is for input tables, and one is for output tables. And those input tables are the dictionary tables, and there's publication on the master and subscription on the slave. So whenever I change or load another table on the master, it will be automatically pushed to the slave or more slaves. And on the other hand, when those threads are running on the slave too, then it will produce the output local G solution, which will be sucked back to the master using the output publications. Optional, this is optional part because if there with some real live application, there will be lots of data. It will be more perhaps optimal to fetch this via foreign data wrappers. And yeah, and for this to happen, you also have a way to distribute the execution of threads. So this module PG extension threads supports this, and I show you how does it work. Maybe it's time to go back to this, and remember the host name was null, and because the meaning of this parameter is I don't care. So it's left to the system which picks up a server to run it. So in our example, we have 2 servers. but it is administratively disabled because I have one table which have configuration of this cluster. Yeah, and this is the mystery where it does have connection parameters, so I keep it in the table. So, and it also has an extra column enabled, so I can simply enable the slave machine, so it will be now able to receive threads. Okay. We can, for instance, rerun this those idles. Two threads, and now the system should distribute the load on. Yeah, exactly. So we have two threads running. One is running on slave, the other on master. And you could actually see it. From the operating system level that the Postgres processes are running. And so going back to this slide, and the one problem with this configuration is asymmetrical, because PageLogical is unidirectional. It would be more interesting to run this system on a BDR, but I never tested it. When I intend to do so. And now, once we have those two servers connected and enabled, we can simply rerun our solver. We don't have to change anything because we are already parallel. And we don't use this host name specifically, so we let the system pick the server to run. So let me, the same example, the larger example, or maybe this one. Okay, I have to truncate the table. Oh, I didn't. Okay, so one problem with this is that you have to separately truncate the tables on both servers because the replication is only one way, so truncating on master is not enough. But I have actually used this thread infrastructure to do so, and I think it's a clever way. I can show you. I'm having a procedure called cleanup local, which uses truncate table solution, and a procedure cleanup, which actually uses this host table. For each enabled host, we are actually sending this local cleanup and truncating locally the table. So I can have consistent state by calling this cleanup function. Again, this wouldn't have to be done if this was BDR, because the truncate would propagate both ways. And well, maybe we can have another example this time. The other host has also 4 CPUs because this laptop has 8 cores, threads. So we can just maybe run this example, really large example. Okay. And maybe 16. Oh, I forgot to clean up. Okay. Okay. Oh, shit. What's up? That's cute. Okay, I think I found a bug with this. Let me clean up. Okay, now this should work. Okay, I'm not gonna debug it right now, so it's not perfect. I told you this is just it's Tatuna's candy. So let's go back to our presentation. So this is visualization of what was just happening. So we have master, which has input publication for input tables to slave. Those threads can be distributed with with thread extension, and they produce the output, which gets published back to the master. So the master has the complete view of output solution and can print it. So we finally got to the last page of our presentation. So the conclusions. So Postgres is inherently parallel environment. It's a powerful computational environment. It already supports out of the box, in many contexts, parallel workers. But in this particular example, it wouldn't be possible to use out of the box parallelization because there's an application domain which users need to identify the parallelization, and we can use this extension to actually support it. It's user-assisted parallelization, so to say. And we can scale up and out using this thread extension and logical replication and sharding. I wish I didn't know about dynamic background processes because I could implement this thread extension perhaps more safely using the background processes. This is what I'm going to do in next steps. Also we'll try to use this extension in BDR environment so that I have to have this artificial asymmetric configuration and artificial cleanup stuff. And so I was sort of thesis to prove that this is not a dumb data store, but something much more powerful computational environment, which can become a like main data hub in your data center. Okay, so this is all. So if I have any question, I'm happy to answer. Yes?
I'm sorry, I'm not familiar with BDR.
Oh, BDR is a product of second quadrant. It's a bidirectional replication. Okay. So it uses PG logical for that, but there is also some, right now this is proprietary code, but I hope to release it as open source. Okay. Yes?
I'm just wondering if all those threads that you create now, they share the same connection. So
No. Each thread has its own connection. The Postgres backend becomes a container for the thread. So each time, I can show you maybe the source code, because this extension is partially written in C and partially written in PostgreSQL. At the beginning, it was 100% in C, but I have identified some portion that I can move out of C because it's easier to develop in PostgreSQL. And the thread, this is the C part. So here is the mapping. So I have create thread, then I have create thread internal. So I'm using in-memory structure for holding those threads. Then I use open connection, which is simply a call to here. And this simply returns me connection context, which I which is stored in the memory structure. So, and this is the start query, which corresponds to the start thread, and this is asynchronous API, the send query. So actually, we are not blocking here, so we can go back and work further. So actually, answering your question, each thread has its own Postgres backend behind it.
Just follow up, if you were to pass data between threads,
Using tables. So because tables, those threads are like Postgres sessions, so PostgreSQL sessions, so they can see each other's.
so you have to commit to each thread and then that thread.
Yeah, but yeah, exactly. In 11, in 10 it will be difficult because the function cannot commit. But in 11 you have procedure which can actually use transaction statements. So you can commit and you can roll back inside the code. But in this particular example, they were completely independent. So they were working on. Yeah.
If you need to pass data between threads.
Then you would have to use tables and commit after it.
Okay, but in 10 it wouldn't really work until the thread actually finishes.
I don't understand the question.
Like in version 10, you cannot commit within function.
Yeah,
So
yes. Yeah, but this is exactly what I told you, showed you what is the real code behind it. Once again. Okay. This is the query which is actually executed in the asynchronous call. So it starts with a transaction. Then I'm calling this thread procedure. It can do some stuff. And after it finishes without exception, this start thread is called. This happens inside the same block, so it can update the status of the thread. It's finished. And and finally I'm committing here, because this happens not in the calling thread, but in the context of a running thread. So, and this is called from the C, so I can actually commit in it. Yeah. So this post start is a kind of like initialization code. You have in C, you have main routine, and before this main runs, there is some initialization. And after main completes, there is some finalization. So it's exactly the same. So there are a couple of these routines: press start, post start, and etc. I can show you. Okay, that's here actually. So pre-create actually insert the row in this thread. Also, there's some logging. Press start, insert some logging, and updates this thread to running. And post start, which is called after the thread procedure finishes, updates state to finished. And this is done in a remote thread, so to say, within the transaction, so another session can see the state change. yeah, it's a bit complex, but okay, this was